In inferential statistics, there's often times when we want to compare two population means. If it's a setting where the way that we are sampling have some sort of connection between like a before and after, or identical twins, or the same person doing a process maybe with different hands, maybe their right hand and their left hand, there could be a lurking variable if we just did it as a cluster of numbers for the first sampling and a cluster of numbers for the second sampling. So then we want to do actually what's called matched pairs when we're doing the information in the data. And to do a hypothesis test for the means, when we're doing it with matched pairs, we actually approach it a little bit differently than if they were just sampling from two groups and they were independent samples. This video is on a comparison of two means when we have matched pair data. So here it says a marketing consultant was hired to visit a random sample of 8 restaurants from a large franchise chain. The net sales for 2 months after applying the consultant's recommendations were recorded in thousands of dollars. So then we have store 1, 2, 3, 4, 5, 6, 7, and 8. And they did information from before their visit with their net sales and then after the visit for their net sales. And for store 1, this is the data. For store 2, this is the data, etc. So the data is in matched pairs. And of course you can see why it would be important to do this, because you have sales of your restaurants are going to be dependent on the clientele you have in that region and the habits and things. So we have that particular setup. Now we still at this point in time don't know what it is that they're going to want us to do with this data. With all of these problems, one of the key things is the setups will look very, very similar. So it's not the setup that actually helps you determine what you're supposed to do in the process that they're asking you to complete. You need to really read the question and then determine it from that. So here it says, do the data indicate? So do the data indicate, test the hypothesis, any sort of thing like that is telling you to do a hypothesis test. That the average net sales, so average net sales, that's why we're doing it with the means, improved. And our alpha, our level of significance, is 0.05 that they want us to use. So it's a hypothesis test. With a hypothesis test, we need to set up our null and our alternate hypothesis. And we need to be very careful to use the correct parameter and the way we're supposed to set that up. Now the thing that gets a little tricky with the matched pairs or with the two groups is that, especially with the matched pairs, what we're going to do is we're going to find the difference between the values in the pairings. So the difference between these two numbers, the difference between those two numbers, the difference between those numbers, etc. And we're going to then do a hypothesis test on the differences. So it depends on which way you're doing your subtraction to which way you're going to set up your alternate hypothesis. So you have to determine ahead of time what it is that you're going to do in your subtraction, and then how that reflects the idea of what it is that you're supposed to set up for your alternate hypothesis. So for example, if I want to know if the data indicates that the sales improved, the top numbers are the before visit and the bottom number are the after visit. If I'm trying to test if the sales improved in general without looking at individually the numbers, I want to see if the after numbers are bigger than the before numbers, because sales improving means your sales got bigger. Okay, so if you subtract before minus after, and your thought is testing whether the after, if you subtract after minus before, and you're testing if the after are bigger numbers, you want to think big minus small. Well, big minus small is a number that's bigger than 0. So say 8 minus 2, that's 6, that's bigger than 0. Big minus small is a number that's greater than 0. Now, if you're testing to see if the sales improved and you subtract before minus after, then you'd be theoretically subtracting small minus big. And small minus big is a negative number. Okay, so I'm going to choose to do my subtraction of after minus before. So I'm going to choose to do my subtraction after minus before. Personal choice, but by that personal choice, I have to set up my alternate the way that it should be. So it's mean, and it's the mean of the differences. So my alternate hypothesis is that the mean of the differences, I'm choosing to go after minus before. So if I'm seeing if they approve, that would be theoretically big minus small, and big minus small is a positive number. Indicating a positive number with an inequality is greater than 0. So then your alternate hypothesis, remember that always has the parameter equal to the same number that's been used in the alternate hypothesis. So my null hypothesis is mu sub d is equal to 0. And we're using the sub d because it's the mean of the differences. Okay, so what we do then is we are going to do the differences of after minus before. So if I take 71.4 and I subtract 67.8, I get 3.6. If I go 102.5 minus 96.9, I get 5.6. 42.5 minus 36.1 is 6.4. And then if you go through and here 48.7 minus 51.9 is a negative 3.2. And then 3.8, 8.5, negative 1.1, and then 7.6. So theoretically, we're seeing overall globally if my sales improve, but that doesn't mean it would happen for every single individual store. So sometimes you might get a negative, and if you do, then you need to make sure you enter it that way. Now, one thing that we can do for this is we could actually now use our TI 8384 calculator, and we could enter each of these numbers into L1 and then do a t-test on that L1. So if we do then the t-test on that list where we entered those numbers, we have a screen that will ask us for data or stats. We're going to put data in because, or enter data because that's what we put in is our data in L1. And then we have our mu sub 0 with a colon, and that's what you have the mu equal in your null hypothesis, so that's 0. The next thing it'll ask you is for your list. And our list, if we put our differences in L1, is L1. And then make sure that the frequency just has 1 after it. And then in your work with your alternate hypothesis, it'll say mu. And when you want to say is greater than mu sub 0. So you want this inequality symbol to match what you did in the alternate hypothesis. And then calculate. And once you do that, you'll get a t-value of 2.67 and a p-value of 0.016. Now we can then finish off the hypothesis test work by either sketching our distribution and finding the critical value for a right tail test and going through that process, or by your p-value compared to your alpha. Now with these, we're going to go ahead and think about the p-value compared with the alpha. So remember, if you're working with the p-value compared with the alpha, if the p-value is low, the null must go. So I compare my p-value with my alpha. So since the p-value is less than the alpha, so 0.016 is smaller than 0.05. So my p-value is smaller than my alpha. When the p-value is smaller than alpha, you reject the null hypothesis. And if you reject the null hypothesis, then your data is significant to indicate the alternate. And the alternate was stated this way because it reflects what it asked me to test. So then we would write our sentence that would say, at the 5% level of significance, always state your level of significance, reject the null. You want to state whether you rejected the null or not. We never accept the null. We either reject the null or we fail to reject the null. So at the 5% level of significance, since the p-value is less than the alpha, we reject the null. And if we reject the null, the data is significant to indicate that the average net sales improved. So you would want to write that sentence out. And that would complete your process of doing a hypothesis test with